When we talk about making an artificial intelligence smarter, there's almost this automatic assumption that we just need to build a bigger brain.
Right. Yeah.
Like, we picture these massive, sprawling server farms, warehouses filled with blinking lights, consuming the power of a small city just to add, I don't know, a few billion more parameters to a model. We've basically been trained by the tech industry to think that bigger is always better.
Oh, absolutely.
Yeah.
I mean, the narrative for the last few years has been entirely about scale,
Yeah.
more data, more parameters, more compute power. It's been an arms race of sheer brute force size.
Right. But what if we could get state-of-the-art capability from a tiny AI that just pauses to think? Welcome to the deep dive.
Glad to be here.
To you, the learner, listening right now, if you've ever worried about your data privacy when pasting a sensitive email into a cloud AI translator, or if you're just insanely curious about how AI models actually go about the business of reasoning, this is going to be a massive aha moment.
Yeah, it really is.
Our mission today is to unpack this fascinating new state-of-the-art paper on GenAI. It's called LatentMT Machine Translation with Latent Reasoning. And we're going to explore how looped language models might completely change how we run AI.
Yeah, it's a radical pivot in how we engineer these systems.
Yeah.
To really grasp why LatentMT is so revolutionary, we first kind of have to look at the current standard for getting an AI to reason through a complex problem.
Okay, lay it out for us.
Right now, the industry heavily relies on something called explicit reasoning or chain of thought.
Right, chain of thought. This is when you ask an AI a hard question, and before it gives you the final answer, it prints out all of its intermediate steps, right?
Exactly.
It generates token after token, explaining its math or its logic out loud before finally giving you the conclusion. It creates this literal trail of text.
And the AI uses that actual output text as an external scratchpad. It literally has to generate those visible words to hold on to its train of thought, because it can't hold complex logic in its active memory all at once.
Wow, okay.
Now, that works fairly well for solving math word problems, but when you apply that explicit reasoning to something like, say, machine translation, it creates a massive bottleneck.
Okay, let's unpack. This isn't seeing the AI scratchpad actually a good thing.
What?
I mean, think about doing long division on paper. Writing out all those intermediate steps keeps you from making a dumb mistake, right? Plus, for us as users, isn't that scratchpad crucial for auditing the AI? Like, if it does all its thinking in some hidden, invisible loop, how do we know it's not hallucinating or making a terrible logical leap?
That is a very fair point regarding transparency. Having an audit trail is great for developers debugging a model. But think about the resource cost for a moment.
Okay.
If you ask a human translator to translate a single sentence from English to Mandarin, you just want the Mandarin sentence, right?
Obviously.
You don't want them to hand you 3 pages explaining their grammatical choices, the cultural context of the idioms, and a list of synonyms they rejected before finally giving you the actual translation.
Right. When you put it like that, yeah, that would be incredibly frustrating for an end user who just wants to read a foreign FNU.
Exactly. And from a computational standpoint, it is incredibly expensive. In the architecture of an AI, generating a token printing a word to the screen is one of the most resource-intensive things it does.
Oh, wow.
Explicit reasoning scales computation along the output sequence. More thinking equals a much longer output, which means more time and way more server cost.
And this new paper fixes that.
What's fascinating here is how LatentMT takes a completely different path. It uses what we call looped language models, or loop LMs.
Looped, so it's feeding information in circles instead of printing it out. What does that actually mean mechanically?
It scales computation along what we call recurrent depth. Let's break down how an AI actually processes text. When you feed a sentence into an AI, it doesn't think in English words.
Right.
It translates those words into vectors, massive list of numbers called hidden states that represent the meaning and context of the text.
Okay, so a hidden state is essentially the AI's mathematical representation of a concept. It's kind of like the numerical vibe of the sentence.
Yeah, that's a really good way to put it. Normally, the AI pushes those numbers through its neural network once and immediately translates them back into an English word to print on your screen.
Just a straight line.
Exactly.
Yeah.
But a loop LM takes those hidden states, and instead of spitting out a word, it loops those numbers back through its own internal architecture. Specifically, its transformer hidden layers multiple times.
And just to ground that term for the learner, a transformer layer is essentially the filter in the AI's brain that looks at all the words in a sentence and figures out how they relate to each other, right?
Yes.
It connects the subject to the verb, figures out the pronouns, things like that.
Correct.
Yeah.
So instead of generating an external scratch pad of text, the AI does all its intermediate computation internally in a continuous state of numbers.
So it's just swirling the math around.
Basically, yeah. It runs the math through those shared relationship filters over and over. No extra parameters are added to the model, and no wasted output tokens are generated. It deeply internally refines its mathematical understanding before it predicts the very next word in the translation.
It's literally pausing to think before it speaks, but entirely in the realm of math.
Exactly.
I want to know how the researchers actually built this. Cause a theoretical concept is one thing, but we want to see the engine they built to test it in the real world.
They built it using a surprisingly small foundation. They used a model called Oro 2.6b thinking.
2.6 billion.
Right. Now, 2.6 billion parameters might sound like a massive number to someone outside the tech space, but in the current landscape of generative AI, that is a tiny model.
Oh, absolutely. I mean, we're used to seeing foundational models from the big tech companies with 70 billion, 100 billion, or even over 1 trillion parameters. A 2.6 billion parameter model is an absolute featherweight.
It really is. And, crucially, they kept that backbone model frozen.
Frozen, meaning they didn't fundamentally alter its core intelligence or retrain its base weights.
Exactly. To make it act as a translator for specific languages, they attached tiny swappable modules called LoRi.
LoRa. That stands for low-rank adaptation, right?
Yes, exactly.
Okay, let me try an analogy here to make sure I'm getting how this interacts with a frozen backbone.
Go for it.
It's like buying a basic, lightweight video game console. Like the console itself, that 2.6 billion parameter frozen backbone handles all the basic logic, the graphics processing, the memory.
Right, the core systems.
But the console out of the box doesn't know how to play chess or, race cars. You don't buy a whole new console for every game. You just snap in a tiny game cartridge for a specific task.
That's a great comparison.
So here they have one baseline engine, and you just snap in a tiny cartridge for Chinese or a cartridge for Arabic without copying the whole engine.
That is a much more accurate way to visualize it. You don't have to duplicate the massive engine for every language pair you want to support. You just swap the tiny LoRa module. And the results they got with this specific setup are frankly staggering.
How so?
They tested LatentMT across 32 different translation directions.
Wow, 32. That includes a massive variety then. We're talking high-resource languages like Chinese, mid-resource languages like Egyptian Arabic, and probably a whole suite of low-resource languages where training data is just super scarce.
Yes, all of the above. And here is where the looped reasoning really proves its worth. The base RO 2.6b model had almost zero exposure to the Chinese language during its initial pre-training.
So it didn't even know Chinese.
It essentially didn't know the language existed, yet when they attached the Chinese LoRa module and allowed the model to use its latent reasoning loops, it achieved state-of-the-art results. It matched or even beat non-looped models that are 3 to 5 times larger.
Wait, really? It beat models 5 times its size? What models are we comparing it to here?
They tested it against models like Qwen38b, which is an 8 billion parameter model trained under the exact same conditions.
Incredible.
And it even held its own against highly specialized 14 billion parameter literary translation models. The latent loops allow this tiny non-Chinese speaking backbone to reason its way to top-tier translations.
That really proves that the cognitive heavy lifting is happening inside those hidden recurrent loops, which, brings up a very tempting thought. If doing this loop twice gives a boost in translation quality, my immediate instinct is to just run it through 1,000 loops. Like, let it sit there and think for an hour. Does it eventually write a flawless Shakespearean masterpiece? Does it just scale forever?
That is the logical extreme, and the researchers tested that exact boundary. They made the number of recurrent steps an experimental variable in their data.
Yeah.
They labeled this variable U.
Okay, U for the number of loops.
Right. They swept this variable from U equals 1, which is just a standard single pass through the network, all the way up to U equals 6.
Let's look at the actual data on how this performs, because the way it scales is fascinating.
It really is.
For the high-resource data set, so that's translating from English to Chinese, the biggest jump in quality happens early, right? Moving from U equals 1 to U equals 2 adds a massive 7.65 BLEU points. But before we go further, let's ground that term for the learner. What exactly is a BLEU point?
So BLEU stands for Bilingual Evaluation Understudy. It is essentially a score from 0 to 100 that measures how closely a machine's translation matches a translation done by a professional human.
Got it.
In the world of machine translation research, a jump of 1 or 2 BLEU points is considered a very significant hard-won achievement.
So a jump of over 7 points just from letting the AI loop one extra time is a massive leap in quality.
It is an enormous gain. But the mid-resource data is even more telling. They tested it on an English to Egyptian Arabic dataset, the Artisan multi-genre dataset.
Okay.
The out-of-the-box, untrained backbone model running a standard single pass was completely useless here. It scored a BLEU score of near 0.00.
Literally producing gibberish.
Total failure. But when they applied LatentMT, the score jumps from 15.35 at U equals 1 all the way up to 24.47 at U equals 4.
Oh, wow.
It actually beat a heavily fine-tuned Google neural machine translation model. But to answer your earlier question about running it 1,000 times after U equals 4, the score basically flatlines. It stays hovering around 24 even at U equals 5 and U equals 6.
Here's where it gets really interesting. It hits a ceiling. It reminds me of proofreading an email.
What do you mean?
Like, think about writing a highly sensitive email to your boss. Your first read through, so that's your U equals 2, you catch all the glaring errors, the missed words, the obvious typos.
Yeah, you fix the big stuff.
And then your second read through, maybe you polish the tone so you don't sound too aggressive, but by the 5th or 6th time you read that exact same email, you're just staring at commas. You're swapping the word happy for glad and back again. The benefit of reviewing it has completely saturated.
That captures the human experience perfectly, and the AI experiences a mathematical version of that exact phenomenon. The early gain-then saturation pattern proves that latent reasoning works beautifully, but the marginal returns heavily concentrate in the first few computational steps.
But I want to understand why it saturates mechanically. Why doesn't the AI just get confused and spit out a totally different translation on loop 6 than it did on loop 5? How does the loop actually refine the thought?
It comes down to probability smoothing. In the first loop, the AI's internal mathematical guess about the sentence might be blurry. It's juggling multiple possible meanings.
Right, it's unsure.
But when it feeds that blurry mathematical state back through its own transformer layers, the layers act like a sharpening filter. It drops irrelevant context, it weighs the grammar rules more heavily, and it sharpens its mathematical focus on a specific translation vector.
I see.
By loop 4 or 5, that probability distribution is so incredibly sharp and focused that pushing it through the filter again simply doesn't change the numbers anymore.
Let's get even deeper into the brain of the machine on that point. How did the researchers actually measure that the AI was stopping its internal debate?
They looked at two very specific internal metrics: cosine distance and the top one flip rate.
Cosine distance.
Think of the AI's internal thought at any given step as an arrow pointing in a specific direction within a vast, multi-dimensional space. Every concept or word has a coordinate. Cosine distance measures the angle between the arrow at loop 1 and the arrow at loop 2.
So if the arrow swings wildly to point at a completely different coordinate, that's a big cosine distance, meaning the AI drastically changed its understanding of the sentence.
Exactly. And what the data shows is that at transition U equals 6 on the DRT dataset, the mean cosine distance falls all the way to 0.014.
Meaning the arrow is barely trembling, it's completely locked in.
Yes. And the second metric, the top one flip rate, measures how often the AI literally changes its prediction for what the very next word in the sentence should be.
Right.
By the sixth loop, that rate drops to just 0.039.
So it's changing its mind about the next word less than 4% of the time?
Its internal representation of the translation has stabilized, the token preference has settled. Pushing it through another loop is just wasting electrical compute power.
Which perfectly explains why the BLEU scores plateau. The internal math heavily backs up the external output we see. But, relying purely on automated scores like BLEU can sometimes be a trap, right?
Oh, for sure.
Cause an AI can technically game a mathematical metric while still sounding completely unnatural to a human reader. Did they actually have real people verify this?
They did, and it is a crucial part of the paper. They used the LQM framework, which stands for Language Quality Evaluation.
Okay.
This involves native, professional linguists manually reading and checking the AI's translations for errors. And the human validation mirrored the mechanical data beautifully.
The paper includes a specific example of this human validation that I think really brings all this abstract, multidimensional math to life.
Oh, the poetry example.
Yeah. The English source sentence they asked it to translate was a very dramatic literary line. Cruel to deny me one ray of those adorable eyes.
That is a notoriously tricky sentence for any machine translation system. It's not a literal statement. The AI has to understand tone, heightened emotion, and the metaphor of eyes casting a ray.
Right. If you translate that literally, it sounds like a science fiction weapon or something.
Exactly.
At U equals 1, the standard single pass, the model completely hallucinates. It produces a disjointed translation that the native speakers flagged with critical severity errors. It totally missed the emotional core of the metaphor.
It just couldn't grasp it.
But they didn't change the model's weights. They didn't give it a better dictionary. They didn't add more parameters. They just let it loop internally to U equals 3.
And the result?
At U equals 3, it produced a flawless, error-free translation. The critical errors completely vanished. It correctly interpreted the poetic nuance of the ray.
Yeah.
It just needed to sit with the numerical representation of that thought for a microsecond longer to grasp the nuance.
Which leads to a profound realization about AI architecture. It means the capability to understand that complex metaphor was always there, dormant within the 2.6 billion parameter model's weights.
Wow.
It just lacked the computational depth to extract it on the first try.
Okay, so we have a tiny 2.6 billion parameter model that acts like an 8 billion or 14 billion parameter model just by running its internal math a few extra times. But let me play devil's advocate here for a second.
Sure.
If we're taking a tiny model and forcing it to do its mathematical calculations 3 or 4 times per word, doesn't that cancel out the efficiency? I mean, running a tiny model 3 times might cost the exact same amount of time and server memory as just running a massive model once. So what does this all mean for the real-world payoff?
That is the crucial engineering question. And it comes down to a very specific breakdown of how AI consumes memory and time. We have to compare LatentMT against the giants, like the 8 billion parameter Qwen3 model on that DRT dataset. The secret to LatentMT's efficiency is that it does not spit out that long chain of thought reasoning text. Generating visible output tokens is actually the most memory-intensive and time-consuming part of running an AI.
Because it doesn't have to print the scratch pad?
Exactly. The researchers conducted a strict efficiency analysis and found a highly cost-efficient knee point at U equals 2. Operating this looped model at just 2 recurrent steps drops the peak inference memory by 52.2% compared to running the larger Qwen388B model.
Wait, it literally slashes the required operating memory in half?
Yes. And because it isn't generating those external scratchpad words, it cuts the end-to-end latency, the actual wait time for the user sitting at their keyboard, by almost 62%.
That's huge.
All while retaining nearly 98% of the peak translation quality of the much larger model.
So it's twice as fast, half as heavy to run, and still retains state-of-the-art smarts.
If we connect this to the bigger picture, this unlocks massive implications for what the tech industry calls edge computing.
Edge computing, meaning running the AI locally, right on your own physical device, rather than beaming your data up to a server farm in the desert somewhere.
Exactly. Think about the current paradigm of AI translation. If a hospital needs to translate sensitive medical records, or a business is translating confidential contract negotiations, or you're just translating private text messages on your phone.
Right.
Right now, you usually have to send that text via cloud APIs to a remote server owned by a major tech company.
Which is a huge data privacy risk. Once that sensitive medical record leaves your hospital's secure intranet, it's out there on a server. You kind of have to trust the cloud provider completely.
But LatentMT's drastically reduced memory footprint, combined with this massive boost in reasoning power from the hidden loops, changes that dynamic. It means we can deploy highly capable, state-of-the-art translators locally. You can actually run this on a standard smartphone or a local hospital server.
Because you only need the processing power to run a 2.6 billion parameter engine and a tiny LoRaWAN cartridge. You don't need a $100,000 supercomputer rack.
Right. It completely brings privacy back to the user.
Yeah.
All the data stays on your device.
Yeah.
Furthermore, it gives high-quality translation access to communities in low-resource environments that might have incredibly unreliable internet connections.
Wow.
They don't need a fast connection to the cloud anymore. The intelligence is localized.
That right there is the real aha moment of this whole paper. We're taking the immense power of massive cloud computing and shrinking it down so it fits in your pocket or on an offline server, simply by teaching the AI to process its thoughts in loops rather than demanding it print out everything it thinks.
Perfectly said.
So, to recap the journey we've been on today for you, the learner, we looked at LatentMT. It's a highly efficient 2.6 billion parameter model that uses looped hidden states instead of bloated parameter counts or long explicit text trails.
Yeah.
By doing its reasoning internally, it hits a Goldilocks zone of early computational gains, smoothing out its mathematical probabilities to deliver highly accurate translations that are private, computationally cheap, and incredibly fast.
It is a masterclass in algorithmic efficiency.
Yeah.
But it also leaves us with a much deeper philosophical takeaway to mull over as an industry. We have just seen empirical proof that an AI can achieve a sudden massive breakthrough in its cognitive quality, grasping poetry, human emotion, and complex metaphorical grammar just by internally relooping its own thoughts a few times before speaking.
It's pausing to reflect, refining its understanding before it commits to an answer.
Which raises an important question for the future of this technology. As we push toward artificial general intelligence, maybe the true secret to human-like reasoning isn't about building an infinitely massive brain. Maybe it isn't about scaling up server farms until we literally run out of electricity to power them.
Yeah.
Maybe the secret is simply teaching an AI the deeply human art of pausing to reflect before it opens its mouth.
I think we can all take a lesson from that. A little reflection goes a long way, whether you're a neural network or a human being. To the learner listening right now, thank you for joining us on this deep dive. Keep questioning the sources around you, keep looking under the hood of the technology you use, and next time you assume that bigger is automatically better, remember that sometimes the most profound insights come from just taking a microsecond to think a little harder. We will catch you next time.